When we first were talking to our friends at Lockheed, it seemed like magic. Like they said, pick an asteroid, Dante, and we'll bring samples back to the Earth for you to study in your laboratory. I was there when it was nothing but a PowerPoint on a slide in a proposal that we were submitting to NASA with this dream that we were going to bring back samples from Bennu.
We are moving to questions. We are going to take a few in the room.
How can these OSIRIS-REx samples help scientists in the future?
Those are going to be a treasure for scientific analysis for years and years and years to come, to our kids and our grandkids and people that haven't even been born yet. It's going to be absolutely incredible.
The key objective for me, and one of the driving objectives of this program, is to try to understand, did carbon-rich asteroids like Bennu deliver the compounds that may have led to the origin of life on our planet, the origin of Earth as a habitable world?
The scientists come up with these grand questions that they're striving to get answers for. We as engineers, for goodness sakes, it's the best job an engineer could ever have, to help a scientist go gather this knowledge. It's just so thrilling and rewarding.
All right, we'll go to the next student question.
Hi, my name is Tadeo Garcia. I'm from Didi Middle School, and my question is, ¿Cómo consiguieron con el nombre de OSIRIS-REx? How did they come up with OSIRIS-REx name?
I think that one's my fault. But when I was first invited onto this program in 2004 by my mentor, Professor Michael Drake, who was the director of my laboratory.
I'm still very much personally guided by John Kennedy's comments when he directed the United States to send a man to the moon and return him safely to Earth by the end of the decade. In that same speech, he went on to say, we choose to do these things not because they are easy, but because they are hard. Well, spaceflight is hard, but we have been very careful to assemble the best navigation team on the planet. And I can make that assertion with confidence.
And he invited me to be the deputy principal investigator on a proposal to NASA for an asteroid sample return mission. And, you know, I kind of looked at the phone and I couldn't believe the words that were coming out of the earpiece, right? I was like, this is amazing. And also daunting, right? Because there's a lot of teams that are going after these kinds of missions. So it's a pretty risky venture, especially for an untenured young professor to buy in. This is an all-consuming effort, right? If you're going to win, this is what you're doing. You're writing that proposal, you're learning how a spacecraft operates, how you manage a giant NASA mission of this magnitude. But I couldn't say no. And the real reason was that my science demanded it, right? I've been studying meteorites for well over a decade with a key interest in what's called the exogenous delivery hypothesis. That is, did these carbon-rich asteroids deliver important organic compounds to the early Earth that triggered the origin of life? And as we studied meteorites in ever greater detail, we realized that we had just reached the limit because they're contaminated. And they're also biased. The atmosphere filters out the most fragile and friable material, leaving only the strongest to make it down to the surface of the Earth. So I knew if my science was going to progress, I had to sign on to an adventure like this. Plus it was too cool to say no, right? I was like, how often do you get a phone call like that? And so let's go, let's get it done. And we wrote a proposal in 2004 and got rejected. And a proposal in 2005, and we made it to the next round, what's called Phase A in NASA's competition, and then got rejected. And then in 2008, the New Frontiers opportunity opened up. And I kind of knew at that moment, as soon as carbonaceous asteroid sample return was on the list, that it was ours to lose. And so sure enough, in 2010, we made it to Phase A. And in May of 2011, we got that amazing phone call that we were going to fly.
The last thing we really wanted was something that was going to excite the public. This mission is exciting.
It's hard to talk about Mike. You know, we lost him about 4 months after we won the contract. And He had been sick for a while up to that point, in and out of the hospital, had liver transplant surgery. He would be so proud of us right now. I mean, he was there to see us win. We were there at his house celebrating. He was extremely excited. He knew not only was this important for science, but for NASA, for the United States and the University of Arizona, and the legacy that he had established as the director of that laboratory. So, you know, we honor him in many different ways. There's a plaque on the spacecraft to his memory. And I think about him all the time. And I feel like he's there with me on the big moments, and he's really proud. But what Mike said was, Dante, I want you to lead the science on this program. And I wrote down 4 words that I thought captured the essence of asteroid exploration. Origins, because we're interested in the origin of life, the origin of the Earth as a habitable world, and the origin of our solar system. Spectroscopy, because we study asteroids mostly with telescopes. And spectroscopy is what happens when you take light and you break it like through a prism into its different colors, and the way it reflects at each color tells you about the minerals on the surface. And by bringing a sample back, we can tell, did we get it right or not? Then I wrote down resources, because I was thinking, I'm a science fiction fan, I'm thinking asteroid mining, maybe somebody will use the OSIRIS-REx information to go and start furthering human exploration by using the resources that are there in outer space. And the last thing I wrote down was security, because Bennu is a potentially hazardous asteroid, and I said, oh, I got OSRS. If I just buy a couple vowels, I can get OSIRIS. So spectroscopy became spectral interpretation, resources became resource identification, and then as the mission grew and got bigger, I decided we needed something stronger than just OSIRIS, and somebody, almost as a joke, said OSIRIS-REx, and we all laughed, and then I went home that night and I was like, that sounds really cool. And so I was like, we gotta be OSIRIS-REx, and I came up with my backronym, which is the Regolith Explorer. Regolith is what we call the loose material on the surface of these airless bodies, and OSIRIS-REx was born.
Being involved in the OSIRIS mission is really awesome. It is giving me the opportunity to do something that I would like to do as a career, which is do spacecraft instrumentation. The student team is going to be, several engineering students and software students building some component of a spacecraft. I got my start as a student, and having the opportunity to just continue to ask questions and then figure out how to design experiments to address those questions and see that unfold over the course of almost 2 decades now, it's really incredible. I'd say on a personal level, it has been this massive experience in confidence building. So you can imagine working on things as a student, you kind of have no idea what's going on. A lot of learning to trust myself, trust my gut, build a team, figure out who I can lean on, and just, really understanding how to do these incredible, almost impossible things has required a lot of building of confidence.
It's the team that really makes these missions succeed, and quite honestly, it's the best part of being a part of a program like this, because it's much bigger than any one person. I can tell you at the peak when we were building the spacecraft back in 2015, there were over 450 people full-time on the program. Over 1,000 people have worked on this, and probably many more. And I'm enormously grateful for every one of their efforts. We are all OSIRIS-REx.
It is fantastic to be able to return a sample to the Earth. When you design a mission and say have a chemistry lab that you want to build to send to an object to study, you're limited by the space and the power and the data rate and all kinds of other things. You, for example, cannot have a mile-wide synchrotron put on a spacecraft. You need to design your instruments early so that they can be well understood and incorporated. You can't make changes as new discoveries happen, as new technologies are developed. When you return a sample to the Earth, you can take advantage of every new technology developed, of new minds all around the world thinking about new ways to analyze the sample.
We have learned a lot of information from previous missions to asteroids and comets, and we learned from that primarily to spend the time to characterize the asteroid and then practice and simulate your sampling maneuver many times over. We have a unique design where we put this TAG-SAM device onto the surface of the asteroid, and then we blow down high-pressure nitrogen gas, kind of agitate the soil, and then basically scoop it up in a giant air filter. That whole process takes 5 seconds, so it's kind of get in, get the sample, and get out of there.
This actually started as a contest where we wanted to know what is the best way to actually bring back a sample, and it turns out that somebody used a solo cup and an air compressor in their driveway, and that's what actually started the TAG-SAM technology. It's a reverse vacuum.
Our design is to bounce off the surface of the asteroid. In fact, we've got a spring in the forearm of our TAG-SAM device, which is acting literally like a pogo stick to push us off the surface of the asteroid after we make that initial contact. So from everything that I've seen, trying to bounce off the surface of the asteroid is the easiest way to get that material.
Put these very incredible proposals together that you think you've thought through all the nitty-gritty details, and it's an excellent concept, and they don't always get funded, they don't always move forward. Sometimes you miss your launch window. So this is kind of a tough game, right, to play ball. So I feel overwhelming gratitude that everything has worked out so well with OSIRIS-REx. That's not, happenstance. We have a very, very hardworking team that is always sharpening their pencils.
We started formal assembly and test operations in March of 2015. We did that in a clean room because it's so important for us to maintain the pristine nature of the samples. So we had extra controls that were required for us on this mission that we haven't had in the past. We then tested the spacecraft through a series of environments that mimic what it sees from the time that the rocket launches all the way until the sample lands safely in the desert in 2023. We tested it over temperature, we tested it over pressure, vacuum, no vacuum. We tested it in vibration environments, and we tested it through the acoustic environment that it sees during the launch environment. It really took a whole team of people in order to make sure that the efforts were successful.
Good afternoon. My name is Dwayne Brown with the Office of Communications. And if you're just joining us, you're watching a news briefing, pre-launch news briefing from NASA headquarters in Washington. On September 8th, NASA will launch the first U.S. spacecraft that will rendezvous with, study, and return a sample of an asteroid, simply called To an Asteroid and Back.
It's so hard at this point in my life to think about what it means to me, because so much of me is invested in it and vice versa. It's really been just an incredible experience, and I'm so excited for what's going to happen.
second, we'll see the crown jewel coming over here. This is OSIRIS-REx. Rough weather that morning. We were a little bit concerned with some of the storms around and some of the winds that we might see, but it cleared out perfectly for us, and they brought it over, and the winds were calm enough.
Slow, methodical, careful process.
That kind of describes space business in general. And now we have a built vehicle.
We have a vehicle, and it's ready to go.
And now they finished the processing on it. We'll be ready to launch today.
Excellent. Spacecraft safely delivered out to the vertical integration facility, and then it was hoisted atop the Atlas Centaur rocket.
It was. It was a good day to do that.
Yeah.
So we found a window where the winds were down, where the clouds allowed us to do it. We got up there. The ULA guys have all been spectacular as well. Like I said, we've had a really good time here, and we're looking forward to a spectacular launch as well.
1 minute, 21 seconds and counting.
Coordinator, clear to proceed. Launch director, LD is go and you have permission to launch. Proceeding with the count.
What makes you excited about watching a rocket launch?
What doesn't make you excited about watching a rocket launch? I hear that you're gonna feel the shock waves and the sound waves.
T-minus 1 minute and counting.
Status. Range green.
No issues with the range. Everything continues to be go. The final status check of Atlas, Centaur, and OSIRIS-REx readiness will be conducted 25 seconds away from launch. T-minus 40 seconds.
Stable at step 3. $28. 25. Status check. Go Atlas. Go Centaur. Go OSIRIS-REx.
Everyone is go. Standing by for launch. Ten seconds. 9, 8, 7, 6, 5, 4, 3, 2, 1. And liftoff of OSIRIS-REx, its 7-year mission to boldly go to the asteroid Bennu and back.
Bearings look good. Starting beneath pump speeds and check pressures are within family. Repeat chamber pressures have plateaued, begun to ramp off.
Heard the voice of Marty Malinowski. The Atlas has begun a pitch and yaw pretty sure to its planned path.
Control right on
5 degrees inclination from the equator.
SRB chamber pressure is almost plateaued at this point. Party 180, injector pressures are good.
45 seconds into flight.
Program is complete. Boosters throttled down.
And the Atlas rocket carrying OSIRIS-REx has gone supersonic. Standing by to pass through max Q, maximum aerodynamic pressure.
Max Q, hydrates continue to look good.
This is the point when the mechanical stress on the rocket reaches its peak because of the rocket's velocity and resistance created by the Earth's atmosphere.
Signatures look good. current altitude is 14 miles. Downrange distance is 9 miles. Current velocity 2,488 miles per hour. Range track shows vehicle progressing down the middle of the range.
And you see the solid rocket booster jettison.
Separation looks good.
Worked hard to get to this point. The best times are ahead of us. We are going to get to asteroid Bennu. We're going to map it. We're going to pick that site. We're going to get that sample, and we're going to bring it back to Earth in 2023. And so I can't tell you how thrilled I was this evening. It was a wild, emotional ride, thinking of everybody that's with us, that's not with us, and all of the anomalies that we troubleshot, none of those came up. We hit all of our milestones within seconds of the predicts. Really kicked that field goal right down the center of the goalpost. So NASA has done it again, absolutely.
And we are live here at Lockheed Martin in Littleton, Colorado for a truly historic event. In just a few moments from now, NASA's OSIRIS-REx spacecraft is going to actually arrive at the asteroid Bennu.
Yeah, so today is what we call arrival. So when we reach 20 kilometers from the asteroid, what we're going to do is do a burn to put us into the precision flying regime that we'll be doing for the next year and a half or so in order to map and discover all we can about OSIRIS-REx and determine the best possible place to go get a sample of the asteroid and bring it back.
A little nervous, a little excited. I mean, after this burn is completed, we're going to be approximately 7 kilometers away from Bennu at the closest approach. So it's exciting, a little intimidating. There's a lot of feelings going through me right now.
It's going to be the first U.S. mission to return a sample from an asteroid. And in fact, this is going to be the largest sample return since the Apollo program brought back the moon rocks.
This is NASA's first asteroid sample return mission. NASA has had other sample return missions, most famously the Apollo program, which brought back over 300 kilograms of lunar material, which we're still analyzing today to unravel the history of the moon and the Earth-Moon system and the origin of our solar system. But there's been nothing like OSIRIS-REx in NASA's repertoire. I like to call it the daredevil spacecraft, right? We just zipped around this asteroid like a hummingbird. And it's one of the things the microgravity environment does for you, is that you can stop, you can start, you can turn left, you can turn right, you can go into orbit, you can leave orbit. You really can explore the entire near-Earth asteroid environment in exquisite detail with ultra-precision maneuvers on the spacecraft.
Bennu is about half a kilometer across, the size of a mountain. We're going to be mapping this entirely new, unexplored area of the solar system. Today we arrive at the asteroid, and we begin a 1.5-year program to scan and study the asteroid, eventually finding a location in the summer of 2020 to touch down and acquire the sample. The sample, once acquired, is going to be put into a canister, and it's actually going to be returned to Earth. You see here Tag Sam putting the sample into this canister, and then in the year 2023, September 24th, this will parachute through and actually land on the Utah desert. So what we're going to do now is actually go into the mission support area here at Lockheed Martin. So how much time do we have now?
It looks like we have about 40 seconds or so before we start seeing the actual burn.
So just to remind you that we're live here at Lockheed Martin, and we are just about to arrive at the asteroid Bennu and begin proximity operations to study this asteroid, eventually returning a sample back to Earth.
Yeah, it's so exciting. I can't believe we're here. All stations, stand by. Burn has started. Stand by for Bennu arrival. So you can see here we have the Doppler residual, so the burn is occurring because I'm seeing the change in velocity from the spacecraft.
It's going to be very quiet here. Everybody's just good.
We have arrived.
You may have noticed we were doing a bit of an unusual high five there. That's called the tag five, because that's reminiscent of the TAG-SAM arm that's eventually going to retrieve a sample.
So we are here. We have arrived at Bennu. Arrival was officially December 3rd of 2018, and that was a morning I woke up and saw an event on my calendar that I put there a decade ago. So it was truly a great day for us. And a lot of the uncertainty has been removed about this mission, right? One of the things that's characteristic of OSIRIS-REx is that we're going to a target that we've only seen through our telescopes. Arrival is one of the greatest moments of my career. I remember the very first images that came in. And, we had been targeting this asteroid since 2005, so over 13 years of planning and plotting and dreaming about this asteroid. And we first saw it just as a tiny point of light moving across the background star field. And if you didn't know what you were looking at, you would never have spotted the asteroid because it looked like just any other star. But we all knew exactly where to look in that image, and then as you started to blink and you saw this thing move across. And I will never forget that feeling. It's like, it's real. It's really there. There really is something in space, and we know where it is, and we're on our path to rendezvous with it.
The OSIRIS-REx spacecraft has been navigating around Bennu for about the last 2 years, studying it in great detail, and also overcoming a number of challenges that Bennu has presented. We were looking for locations on Bennu that were 50 meters in diameter, relatively flat, and covered with fine-grained material. And by fine-grained material, I mean stuff that's the size of a dime or smaller.
As we started to approach Bennu from a distance and it started to fill up the camera field of view, it looked exactly like we thought it would, with a few boulders sticking out. But as we got closer, we expected to see a very sandy surface with maybe a few boulders here and there. And what we saw is very little sand. And we saw these mountains, we saw boulders, we saw rocks, and we saw very few areas that had this sandy surface that we were expecting and what we had designed to.
Well, I like to call Bennu the trickster asteroid. So when we first picked the target, we performed an extensive ground and space-based telescopic campaign to try to understand the nature of the surface. And based on thermal data and radar data and the shape of the asteroid, we convinced ourselves that the surface was composed of fine-grained, sandy, or at worst gravelly-like material. And we expected, and quite honestly sold it to NASA as easy to sample. When we got to the asteroid, we realized that the surface was rough and rugged and covered in giant boulders with nary a beach in sight. And we knew we were in for a real challenge. And we not only had to come up with a new way to get to the surface, but we had to ensure that it would fit within a really tight spot and remain safe while it was collecting that material.
Bennu's rocky surface presented a challenge for the original LiDAR-based approach to the touch-and-go sample acquisition event. As an alternative, the project developed an onboard optical-based approach called natural feature tracking. NFT requires detailed three-dimensional maps of the surface of Bennu. In order to build those three-dimensional maps, we needed many, many images of particular patches of surface on Bennu itself.
And so all these surveys we've done throughout the mission have been at distances between several kilometers from the asteroid down to just a few hundred meters from the surface. And based on those different perspectives and what the shading of that terrain is, it's possible to build a 3D model. Very similar to how we have two eyes that allow us to have depth perception of what we see. NFT requires multiple features across the field of view to have a depth perception.
The original tag accuracy requirement was to touch the surface within a 50-meter diameter circle. Based on Bennu's rough surface, our actual performance has to be much better than that, at 10 meters or less. And even within that 10-meter area, there could be smaller localized hazards that may damage the spacecraft.
Right now, we are working on a flight software patch to help us avoid hazards as we come in for a sample event. When we do natural feature tracking, that is all autonomous on board the spacecraft, where we load the features or a catalog to the spacecraft, so we are telling it where we expect these features to be.
So as the spacecraft makes its progress down to taking the sample, we're recording images and then locating those landmarks to make sure we're on the right track. And if there's any issues with the trajectory or we see landmarks where we shouldn't, we know something's up, then we can back away and wave off the attempt, try again.
As soon as we were dealing with that and processing the challenge that Bennu presented to us, we literally saw the surface explode, erupting particles into the near Bennu environment, and we panicked. And we thought maybe that this was a hazardous environment and the spacecraft was a risk and maybe the whole mission might be lost. And this is where we realized how the microgravity environment can really mess with your mind. What looked like a dynamic, energetic explosion on the surface was simply a little puff of material with flakes of the asteroid gently gliding around, sometimes going into orbit, re-landing on the surface of the asteroid. And it turned out to be an amazing science experiment. So what looked like a major catastrophe turned out to be a great opportunity.
As we were first approaching asteroid Bennu in that fall of 2018, in the December timeframe when we arrived, we could already clearly see there were a couple of interesting areas that, to be clear, none of the places looked smooth, but there were some areas that were a little bit smoother that we could actually see with our eyes just from that visual observation. But then we had to really study them in detail and quantitatively look at, is this possible to deliver the spacecraft? Is this going to be safe for the spacecraft? And are the particles small enough?
One of the most challenging aspects of pulling together that beautiful global mosaic of Bennu was getting the right data to make a mosaic. So before we even had the images that we stitched together, a few hundred in total, we had to make sure that we were taking images of the surface that were lit at just the right conditions so that you could see small shadows that would outline those particles, and also that were taken at sort of a straight on angle, or as straight on as we could do with our spacecraft, so that you didn't get a lot of distortion. Once we had all of that data, you're dealing with hundreds of images. All of these images have, 1 million pixels or more. It took a lot of effort, but it looks like a very seamless map of Bennu. It's also the finest spatial scale that we have ever mapped a planetary object, which is pretty impressive.
We went through a very rigorous sample site selection campaign, and we had 3 driving criteria. We had what we called the deliverability, which is how tight of a spot can we get that spacecraft into. We were looking at craters that were about 20 meters or 60 feet in diameter, just the size of a small parking lot, and the spacecraft's about the size of an SUV. So it was a really tight fit, especially compared to what we originally designed to. The second one was safety. Even if we could get into one of those tight spots, would the spacecraft survive? And we were particularly worried about tipping over and flying away into one of the many giant boulders that dominate the surface of the asteroid. And then the third one was sampleability. if we got the spacecraft there and it was safe, was there anything on the surface for us to pick up? We were looking for particles about 1 inch or 2 centimeters across or smaller. And there's very few patches of material like that on Bennu's surface. So we kind of evaluated all of that. In the background was a parameter we called science value. But the good news was everything on Bennu was scientifically valuable. We saw water-rich clay minerals and we saw organic molecules, which are two of the prime types of material that we were trying to collect. So in the end, we kind of used the basketball tournament analogy, and we started with about 16 sites. We called them the Sweet 16, and we put them up against each other, and we evaluated how much fine-grained material we estimated was there. And we couldn't actually see the fine-grained material, but we could see where the big rocks were not, what we called the unresolved patches of the surface, and we assumed that there was fine particles there that we could pick up. We eliminated half down to the Elite 8 and down to the final 4. And when we had the final 4 sites, we performed a series of low-altitude reconnaissance passes to kind of do a safety check. And that very quickly revealed that 2 of the sites were quickly out of contention. One of them was simply just too small of a crater, and it looked a lot like one of the other sites, so we were able to eliminate it. And the second one looked really good. In fact, I thought it was the leading contender going into that phase, but it turned out to have a lot of fairly large rocks with the fine material interspersed in between it. And that one was gone, so we were down to 2. One we called Osprey, and one we called Nightingale. Both of them about 20 meter or 60 feet diameter craters. One near the equator, Osprey, one in the northern hemisphere, Nightingale. And it turned out to be kind of a contest. Osprey was safer, but Nightingale was more sampleable. And also the science looked better there. It was darker, redder, it looked fresh, like recently exposed, so not modified by the space environment. When we pulled the board, we had a site selection board, my heart kind of sank when Flight System and the Goddard Space Flight Safety engineers voted for Osprey, because I really wanted Nightingale. But the TAG-SAM team and the science team were voting for Nightingale, so it came down to me. I had to make the final decision.
Hello, and thank you for joining us in the booth here at AGU, the American Geophysical Union, for this special edition of NASA Science Live. Today we have a big announcement from the OSIRIS-REx mission. OSIRIS-REx is NASA's first mission to retrieve a sample of an asteroid and return it to Earth. And we're going to find out from where today.
So I stepped away from the meeting, I kind of walked out, and I said, I have to go with the science. Right? I have to go with the science. It's what we came here for.
Dante, do you want to tell us which one you've picked?
I will. So I'll say that just thinking that we're going to get this sample back to Earth sends chills down my spine. So the winner of the OSIRIS-REx Site Selection Championship is the Nightingale site.
All right. Make some noise, audience.
And I want the material from Nightingale almost like it was calling to me. So I made the final decision. We're going to go in. The safety was acceptable. Lockheed Martin agreed that they could sample that area, and the science is what made the decision.
It was a decision that had a lot of stakeholders, and a lot of people had to come together and make their case before a decision was eventually rendered by our principal investigator, Dante Loretta. And so I remember during the sample site selection meeting, Dante turned to those of us who were scientists on the team and asked what our opinion was. And I think I was the first person who spoke, and I was just like, Nightingale. It has the organics, it looks fresh. Like, if we just put our science hats on, that is where the value is.
Nightingale and Osprey were always pretty high on the list, but in my mind, it wasn't clear. We had some fascinating sites to choose from, including a few sites where they were very small sites, but it looked like there was some really fine-grained material there, but clearly they were just too hazardous for the spacecraft.
What is the biggest challenge of the site?
So the biggest challenge of the Nightingale site is those large boulders that are off on the eastern edge of the crater, because that tallest one, I colloquially call it Mount Doom because it has the classic kind of peak shape that we're familiar with from the literature. That's about 7 meters tall, and then when you're down at the bottom of the crater, that's another 3 meters. So we're talking 10 meters or 30 feet So it's a substantial building-sized obstruction, and we're trying to get into a crater that's on the order of a few parking lot spaces wide. So we are doing a really tight job parking that, and we're aware that we have hazards around us. So precision navigation to that sampled material is our biggest challenge.
So all we have left to do to deliver on our promise to the agency is get that sample safely back to the Earth, get it into our laboratories, and answer the fundamental questions about the formation of our solar system and why Earth is a habitable world.
The pandemic has changed the way we lived our lives. Masks and social distancing have become a way of life.
As the whole world was coming to grips with the pandemic in the March timeframe, this team was in the midst of preparing for the checkpoint rehearsal that would take the spacecraft only 65 meters above the surface. So we had to rethink the entire way in which we were going to do that rehearsal with only a skeleton crew here in the building and with many of our team members remote.
I think the hardest phase of the mission was in spring of 2020 when the COVID pandemic hit. It was a scary time. And we were exhausted. And I would say probably by April, about a month after the lockdown, I wasn't sure we were going to be able to do it. And it wasn't because of the technical challenges, but it was the stress and the human factors that I was really starting to worry about.
Now, the main event is happening in about an hour. This is called TAG. Can you explain to us a bit why it's called TAG?
Yeah, today we're tagging an asteroid, and TAG is an acronym that describes our sample collection strategy. We're going to send the spacecraft down for a short duration contact with the asteroid surface, anywhere between 5 and maybe as long as 15 seconds. So we call it a touch and go, or tag an asteroid.
And that sample site we're going for today, Nightingale, it's just a few meters in width. Just take a step back for a second and put yourself in the shoes of some of those engineers on this mission. And imagine trying to park a spacecraft on an asteroid 200 million miles away in a space no larger than a few parking spots. As if parallel parking on an asteroid isn't hard enough, imagine also trying to dodge hazards like rocky boulders as you're making your descent down to collect a sample. And on top of that, the team has actually programmed the spacecraft to steer itself down to the surface.
We mapped the surface of Bennu to unprecedented resolution of 2 centimeters per pixel, which is better than what we've done on our own Earth and Moon. So it was a huge Herculean effort to get to this point where we're comfortable handing the maps and the keys over to the spacecraft to get us down into this small site today.
So right behind me is the MSA, the Mission Support Area for OSIRIS-REx. And today it is filled with very excited people, the scientists, engineers, and technical specialists who've worked on this mission, in some cases for more than a decade. So back there is Gary Napier from Lockheed Martin. He's right in the middle of it all. So Gary, what's the feeling in the room?
Michelle, like you said, I am just right behind you, about 20 feet. We're here in the larger Lockheed Martin Mission Support Area, where we're operating 6 of NASA's spacecraft around the solar system, 4 of them at Mars, 1 of them at Jupiter, and this one right here, OSIRIS-REx.
So it's important to understand that the spacecraft is actually literally on the other side of the solar system, over 200 million miles away from the Earth. So any signal that we were to transmit here would take over 18.5 minutes to reach the spacecraft. So when we get these signals back, we're actually seeing things that happened in the past at the asteroid. Earlier we departed our orbit around the asteroid, so we're flying over the sunlit side of the asteroid, taking images for the onboard guidance system called natural feature tracking. A couple other key events that have taken place already is the spacecraft has deployed its robotic TAG-SAM sampling arm, so the arm is ready, in position to collect that sample. And we've turned on and started collecting science data from one of our science instruments, the OTIS thermal emission spectrometer. The spacecraft has already moved into its second natural feature tracking attitude and is getting onboard positional updates as we speak. And I can tell you everything is going exactly according to plan right now. It looks really good.
Now, remember that this is a historic event. Today's endeavor will be the first time the space agency has ever touched the surface of an asteroid, collecting a sample of this pristine ancient material, a scientific treasure far more precious than gold. Let's talk a bit about why working in this low gravity environment makes it tough to get a sample, because you might think sort of at first you could just take like a robotic claw or a robotic arm and scoop something up, but that's not going to work in these conditions.
That's exactly right. The microgravity of Bennu provides a challenge of sampling that we don't normally face on Earth. You can imagine trying to use a shovel or a scoop on Earth and the ground pushes against you, but the gravity keeps you on the ground. On Bennu, the surface gravity is thousands of times lower than on Earth, so if you pushed a shovel or a scoop into the ground, you'd push yourself right off the surface. So we had to come up with a technique that worked in the microgravity environment and that could work in this tag architecture, this touch and go architecture of just a few seconds long.
So I understand the next big milestone we're looking for here is something called match point.
That's right.
So what happens at match point?
Match point is the final maneuver that the spacecraft performs by firing its thrusters. That's where we become centered over the Nightingale sample site and begin that final descent down to the asteroid surface, and the spacecraft is solely focused on its safety calculation and the decision on whether or not it's going to proceed down to collect that sample.
Attitude control system has transitioned to touch and go mode.
Right, spacecraft's getting ready to make contact with the asteroid surface here.
OREX MSA on OREX off. OREX is descending below 25 meters.
Okay, we're getting really close. And I want to remind you, it's the 5-meter crossing that's the really critical one. We're only a couple minutes away from that. So the spacecraft has one key decision left to make. It's calculating right now the probability that it's going to come down either on a hazardous area, as we defined on that hazard map, or in a safe area. So we may, at 5 meters, the spacecraft may decide that it's hazardous and it's going to back away, allowing us to live to tag another day. So to me, all my senses are on that call out right now.
Yeah.
And I really want to hear that we are go for tag.
Position uncertainty is 0.5 meters. Predicted tag lateral offset is 1.7 meters. Hazard probability is 0%. Tag lateral velocity is 0.2 millimeters per second.
Oh my God.
Tag vertical velocity is 10.2 centimeters per second.
That sounded really good.
Yes.
So it sounded like the hazard map calculation looked really good. We're coming down in a green area.
MSA on OREX off. OREX has descended below the 5-meter mark. The hazard map is go for tag. Contact expected in 50 seconds.
We're going in. We're going in.
Touchdown to tag. Sampling is in progress.
Oh my gosh, we're there, folks. That was amazing. I mean, I don't know if you saw the team here, but they just kind of blew up. It went from being steely-eyed to like celebrating the Super Bowl. Congratulations. How you guys feeling?
Transcendental. I mean, I can't believe we actually pulled this off.
OSIRIS-REx MSA on OREX op. Sample collection is complete, and the back-away burn has executed.
All right, we're on our way The pyro bottle's fired, so tag SAM operated. The back-away thruster is fired, so we're safely moving away from the asteroid surface. The spacecraft did everything it was supposed to do. We did it. We tagged the surface of the asteroid, and it's up to Bennu now to see how the event went. It's almost hard to process everything that's happening right now. It's overwhelming pride in this team and everything we've done to get here. I couldn't really have anything better to say about this group of people.
We are here live after some excellent news. I'm here with an exultant Dante Loretta from the University of Arizona. So one more time for our audience out there, explain when we know we'll have a sample.
A little overwhelmed right now, Michelle, I have to say. It's been pretty intense several minutes here. I can tell you that everything went just exactly perfect, which is kind of the hallmark of this team. We have consistently beaten expectations over and over again. We have overcome the amazing challenges that this asteroid has thrown at us, and the spacecraft appears to have operated flawlessly. We don't know how long we were in contact with yet. That's some reconstructed information that we're going to have to put together over the next few hours as the data come in. We backed away successfully from the asteroid surface. The team is exuberant back there. Emotions are high. Everybody is really proud. We have some work to do to determine how much sample that we have collected. The next thing that I'm going to be looking for is once the spacecraft cools off, it probably got pretty warm as it approached the asteroid surface, so it needs to get rid of some of that excess heat. It's got to get those solar rays back onto the sun and get power positive. Once it's stabilized, it's going to point that high gain antenna at the Earth, and we're going to start bringing that data back. And those SAM-CAM images are going to tell us an enormous amount of information about how the events of today went.
It's going to be a long, hopefully happy night for all of you as more data comes in. Thank you so much. It's been such an honor to be with you.
Thank you. Thank you, everybody, for a great evening. And kudos to this team. It's an amazing experience.
Oh, wow.
And history was made tonight.
Hello, everyone. I'm Nancy Neal Jones from the Office of Communications at NASA Goddard Space Flight Center. Yesterday, NASA's first asteroid sample return mission, OSIRIS-REx, successfully made contact with the surface of asteroid Bennu to collect a pristine sample for delivery to Earth in 2023. To share some remarks with us and to tell us more about what happened yesterday and what's coming up for the mission, we have with us today Dante Loretta, OSIRIS-REx Principal Investigator, University of Arizona.
So yesterday was all about monitoring this real-time telemetry from the spacecraft as we watched the events unfold 200 million miles away. And the question that came up over and over again in that live broadcast was, when are we going to get the images back? When are we going to know how the sampling event went? I can tell you, a lot of us were up really late last night. We were watching the images come down one by one. By about 2 a.m. here, local time in Denver, we got what I call the money shot, where we saw tag SAM contacting the surface, and then the effect of injecting that high purity gas down into the asteroid regolith. I must have watched it about 100 times last night before I finally got a little bit of shut-eye. and then I dreamed of a wonder world of Bennu regolith particles floating all around me.
Well, like everything on Bennu, a nightingale was unexpected in the way it behaved to the contact from the spacecraft. It's fun to go back and look at some of our early animations where you can see the TAGSAM head pushing firmly onto the surface, kind of like hitting a pad of concrete. There's a little bit of grain and dust that gets kicked up. And you know, we didn't make that up. We tested TAGSAM dozens of times, including in microgravity on NASA's C-9B microgravity testing aircraft. And that's what it looked like. TAGSAM pushed down onto the regolith bed, a few little particles floated away, kind of like coins flipping in slow motion. You could hear the rumble as the gravel got ingested into the TAGSAM head, and then when you pulled away, there was a tiny little divot underneath what TAGSAM had excavated. And we really thought Bennu was going to behave just like the test chambers did. But no, it was completely different. There was almost no resistance whatsoever from the asteroid's surface. The TAGSAM plunged in. It was like dropping into a pool of water. And we were deep into the asteroid subsurface even before that gas fired, and we just kept going. If we hadn't fired the back-away thrusters, we think the spacecraft would have just disappeared like into a pool of quicksand. So as a result of that really soft, compliant surface, the gas from TAGSAM and the thruster plumes from the back-away burn excavated an enormous crater, 8 meters or about 25 feet in diameter, way bigger than anything we expected. Our glorious moment, we safely contacted the asteroid surface, bury the TAGSAM head and fire the gas, and you will load that thing up. Turns out we did too good of a job. So, we backed away. 2 days later, on October 22nd of 2020, we put TAGSAM through a photo shoot. All kinds of different camera angles and lighting conditions, just trying to get some hint, was there any sample that was collected in this amazing event? It looked like the TAGSAM head was literally spewing material into outer space, and panic shot through me at that moment. And I was like, oh man, we're bleeding. We're losing sample at an enormous rate. About 10 grams were visible in that one shot. That was, 1/6 of our total mission requirement in a few seconds that we were seeing escaping from the TAGSAM head. The good news was, the reason we were leaking material was because we had collected so many large stones that we were jamming open the safety valve meant to keep everything inside the collection chamber. So we got permission from the agency to go through rapid stow, quickly got the TAGSAM head into the sample return capsule. And fortunately, we were able to go back to Bennu in April of 2021 to get some great imagery and spectral data of the surface to really quantify the nature of that disturbance. When we designed the mission, we did not plan to go back and image the tag site after sample collection. We thought this is such a risky maneuver, get the goods and get out of Dodge kind of approach. But after that amazing and dynamic response of the asteroid surface, I couldn't leave it alone, right? I was like, this just keeps bothering me. We have to understand what we did, and we have to document it for science and for future asteroid explorers to understand why this behaves so differently. When we estimate the strength of the particles that we see on the surface, there's no way they would survive passage through Earth's atmosphere. They would simply disintegrate, forming a giant fireball. So I have high confidence that we're bringing back the kinds of material that literally, physically cannot make it to the surface of the Earth as a meteorite.
All stations, the ADM burn is completed. We have a nominal ADM burn, and we're bringing the samples home.
The science speaks for itself. I mean, we're bringing back hundreds of grams of pristine sample from a body that hasn't been touched and is relatively unchanged since the beginnings of the very solar system. So the benefits to science are just astronomical. But the benefits to engineering, which is really what I'm interested in, is to me just as fascinating. It's like we're really pushing ourselves, the challenges, the things that we can do with the technology that we have. It's demonstrating our ability to deliver something from space to the ground safely and accurately. That's, to me, motivation enough to do these types of missions, well beyond even the science information that we'll gain from it, which is just invaluable to humanity.
And then really, the reason I answered the phone call, the reason I signed up for the mission, the reason I put in all of this hard work is finally going to come to pass. We're going to get pristine samples of carbonaceous asteroid in our laboratories and really go after the big question. Did these objects deliver the seeds of life to the Earth?
I'm not sure it's possible to identify one single person who will be the most stressed out. I'm sure that our principal investigator, Dante Loretta, will be very stressed, but also very, very excited, as this is the culmination for him of almost 20 years of work. But we have so many people on the team who are so invested in this and really, really care about the sample and who have been working on this mission for years and years and years. So I think we're all going to be a combination of very nervous and very excited.
Yeah, we're going into endgame here, you know, after almost 20 years.
So the sample return capsule is landing at the Utah Test and Training Range west of Salt Lake City, and this is an Air Force test range. It's a wide open area, basically a dried salt flat, dried lake bed. It's free of obstacles. It has lots of DoD tracking devices around there, and it's a controlled airspace. It's a great place to bring something back from space where you need a large landing footprint. Right now, we're only 60 days away from the sample landing. We're working on all of the final logistical details of getting all our people out to the site to do the recovery. We just completed a training last week. We're going to do another rehearsal in August, which will be our final rehearsal. A lot of moving parts right now.
When I found out I was going to be the ground recovery lead, I was very excited. It's rare that you get to be involved in some sort of a project that brings something back from space, and to be in a role where you get to oversee all of those operations and make sure that it happens without a hitch is just a really exciting opportunity. And we have to make sure that everybody is trained, that everybody agrees with the way that we're going to do things and is ready to go. And it's been fantastic because everybody's pulling in the same direction and we're ready to recover this.
So a very important requirement for OSIRIS-REx is to get the sample into a clean room as quickly as possible, because we're trying to maintain the pristine nature of the sample and make sure it doesn't get contaminated from stuff that's in the Earth's atmosphere or on the ground at UTTR. So the recovery team is designed to make that recovery happen as soon as possible. There's a couple of technicians from Lockheed Martin, there's a couple of curation specialists from the Johnson Space Center, and there's a couple members of our science team, and then there are 2 members of the Air Force that are our on-scene commanders that are helping us navigate the range. That team will fly out to the capsule landing site on 4 different helicopters, and they each have unique tasks of securing the capsule, making sure the area is safe, sampling, taking soil and air samples from around where the capsule landed to look for possible contaminants, and then get the capsule packaged up as quickly as possible to fly back via helicopter.
So we're very concerned about the safety of the recovery team, and one of the possible things that could go wrong is if the batteries start on fire once the capsule lands. We don't expect this to happen, so one of the first things we're going to do when the capsule lands is one of the Lockheed Martin technicians will go up to it with a sensor to detect noxious gases that would be released if the battery were operating. And if we don't detect that, then we can proceed with the rest of the procedure. If we do, then we have to stand back and wait for the situation to clear. So we fully expect when the sample return capsule to hit the atmosphere that it will release the parachutes and descend slowly at that 11 miles per hour. But there is a chance that if something unexpected goes wrong, that the parachutes won't deploy. In that case, the sample return capsule will have a hard landing. It'll go very fast, it'll hit the ground, it'll likely rupture the sample return capsule. But that's a very low likelihood scenario. We fully expect that the sample return capsule, the parachutes will deploy, everything will work as expected, and we'll get that nice pristine sample in a very protected, enclosed sample return capsule. So the spacecraft is approaching the Earth at a speed of over 27,000 miles per hour. It'll release the capsule at just the right moment to intersect the Earth's atmosphere. We only have one chance to do this. We can't, wave off and do it the next day. If there's bad weather, if there's a snowstorm at the Uter, when we are getting ready to release the capsule, we will still release, and we will do our best to get to the capsule as quickly as possible. But this is truly a critical event. Everything has to happen on time in order to be successful here.
The team prepared for virtually every weather condition that we could think of. A number of our rehearsals we did in the rain. We also wanted to be prepared in case there was muddy conditions, so we actually built a custom mud pit and put the capsule inside of it and practiced recovering it. We also practiced under extreme heat and very windy conditions. So we've made sure that we've practiced in every possible condition that we could see out here today.
Not an optimal scenario, but I think we can operate in it.
On September 24th, the sample return capsule is going to land in Utah at the Utah Test and Training Range. And from there, we will have to track it down a little bit, but we'll be tracking it in flight to get to it as quickly as possible. Our field team will go with helicopters and bring that sample return capsule actually to a portable clean room or temporary clean room we're going to have set up in a building right there in Utah.
The capsule will actually be carried back to a clean room under a sling from the helicopter, a 100-foot long line, and that allows us to pick up the capsule from the ground via helicopter, fly it back to the hangar, and drop it right outside the front door. Allows us to get the capsule into the clean room just as quickly as possible, and ideally within 1 to 2 hours after landing.
We'll actually take off the heat shield and back shell and some other components for safety. And inside of that is what we call a sample canister. The sample return capsule is kind of like a nesting doll. We have these multiple layers of protection. And then that sample canister will have a nitrogen flow put on it, what we call a nitrogen purge. And with that nitrogen purge to protect the sample to keep any incursion of terrestrial atmosphere coming into that canister, it will be flown from Utah here to Houston, Texas. After which point we'll bring it into our building and get it into a glove box and open that canister up to see the tag SAM. And that'll be the first time we're seeing the tag SAM since it was stowed at Bennu.
On OSIRIS-REx, we have activities called Science Operational Proficiency Integrated Exercises, or SOPIs for short. These activities are fully integrated team events where we rehearse critical moments on the mission. In this case, we were looking at a simulant of the sample coming back from asteroid Bennu, making sure we understand the different roles and responsibilities, team member communication, and our priorities and procedures. You can feel the stakes are rising as that sample gets closer and closer to the Earth. I was surprised by the pressure that the team was feeling. As the handlers were dealing with the simulant material, it was clear they understood the stakes, and my presence in the room was probably elevating the temperature, and they were a little bit concerned about that. So I was surprised that I need to do a better job as the leader, kind of damping down, lowering the temperature, making everybody understand how much we respect them, how well integrated this team is, and how valuable they are, so that they can do their job calmly and precisely, taking care to handle that sample really well. And everybody understands the science priorities and the process about how we're going to select individual stones and accumulations of fine particles to get out to the dozens of labs all around the world.
We have a number of different collections. Actually, the first collection that NASA curates at Johnson Space Center was the Apollo collection, the rocks that the astronauts collected on the moon and brought back. So that was kind of the beginning of curation at NASA Johnson. The next collection was the Antarctic meteorites. And we also have had other sample return missions. Genesis, which was an array that captured basically elemental and particles coming off of the sun. The Stardust mission that flew behind a comet with aerogel. I think actually the most difficult thing working in the glove box is basically you put your hands in, but you're only really usually up to at most here, so you lose all shoulder motion. And you'd be really surprised how much you do with your shoulders when you're using your arm. So you really can only work pretty immediately in front of you and a little to the side. You have such a lower range of motion than you normally do. So your colleague right next to you, you'll pass something to them that you maybe normally, when you're sitting at a conference room, you'd be able to reach yourself. But in the glove box, we have to very carefully and coordinatedly, when we have to move things around, pass them to a colleague, think about our movements ahead of time, and think about what our geographic limitations are. So it does require sort of almost a ballet or synchronized swimming. So all of this pre-planning we're doing is also so we can keep the sample as close as possible to the way it was when it was collected at the asteroid and when it returns to Earth, because those are the conditions that the scientists are trying to study when they're studying this sample. So we're really lots and lots of careful control of any materials that might come in contact with the sample, both in construction of the lab, the glove boxes, what goes into the glove boxes, what immediately touches the sample, as well as our role in recovery in Utah. It's a lot of planning on the front side that we're really getting close to the finish line on. Also, afterwards, we continue to really be careful and super protective of that sample to preserve it for decades to come so it can continue to be studied as new instrumentation and scientific methods are developed.
On Earth, when you can bring the sample back, you can adapt to new information, you can adapt to new technologies, and you can use devices which are not small, but in fact enormous, the size of buildings, things that are actually larger than the launch pad, let alone the spacecraft. You can have the fussiest instruments that give you the best data that need babying because you have time and you have people who can make sure the instruments do what you need to get data that's just impossible to get in situ on a spacecraft at the object. So sample return gives you more power, more flexibility, and one of the wonderful things about it is it's available for the whole world who have new ideas and can express them by looking at the sample in their own way, even if they weren't part of the initial team. New analyses that have not yet been invented by people not yet born.
I think one of the age-old human questions, perhaps going back to the beginning of humanity, is, are we alone in the universe? And that maps directly into, why are we here?
We're going back to the dawn of the solar system. We're looking for clues as to why Earth is a habitable world. This rare jewel in outer space that has oceans, it has a protective atmosphere. We think all of those materials were brought by these carbon-rich asteroids very early in our planetary system formation. And of course, the biggest question, the one that drives my scientific investigations, is the origin of life. What is life? How did it originate? And why was the Earth the place that it occurred?
4, 3,
Launching
2,
in 2016
1.
seemed like the highlight of my career at the moment, but it was really just the beginning of getting us to this incredible world, this small asteroid named Bennu. It's a stunning celestial object, and its shape is particularly intriguing. It literally is a droplet made out of rock, gravel, and boulder that are barely held together by their own microgravity. And it was amazing to have our spacecraft visiting this celestial neighbor for over 2 years. We believe that we're bringing back that kind of material.
literally may be representatives of the seeds of life these asteroids delivered at the beginning of our planet that led to this amazing biosphere, biological evolution, and to us being here today to look back on that amazing history, to think about where did we come from?
Before we get into the action, though, tell me, Jim, what are you most excited about?
Lauren, it's the masterpiece of engineering we have here. Just think about this. In 50 years, we've gone from bringing things on the moon back with crews to all robotic sample return for science that's literally beyond words. It's sublime. So we can't wait to see what we're going to learn.
We cannot wait.
Yeah, good morning, Lauren and Jim. It's already been a very bright early morning for all of our team members involved in this mission. Just a little bit further north from us, about 4 hours ago in Waterton, Colorado, the team met to assess the readiness to release the SRC from the main OSIRIS-REx spacecraft.
Approximately 1 minute to release.
Whole country and the whole world is watching.
15 seconds. System says confirmed, step 3.7.011.
My heart stay with you as this precious sample is recovered. Happy sample return day, and congratulations to all who worked so incredibly hard on this mission.
Seconds. 30 seconds. We'll be coming to wake 1 on a move, then cold open, then camera open. Seconds. 10. 7 more. 6. 5, 4, 3. Stand by, cold 2, open. 1.
You're looking at live pictures of the sky above the Utah Test and Training Range. In less than an hour, a 4.5 billion-year-old piece of the ancient solar system will be landing here in the desert. This is live coverage of NASA's OSIRIS-REx sample return.
Very clear skies this morning as well. As we were actually driving out, I saw a shooting star meteor, and in just a few moments, the SRC itself will be streaking across the skies as we begin to track it. Our high-altitude plane is up in the sky, ready to take images in the infrared of our SRC, and we are here, ready to go to cover all of today's mission events. I'm going to be right here with you all throughout the process as we get closer to that entry, descent, and landing. Just a few moments ago, we heard the helicopters take off from here to head out to Wig just at the edge of the landing ellipse.
Recovery operations. Helicopters 1 and 2 have arrived at the holding location.
So good news, our helicopters are ready to go and begin those recovery operations just as soon as we have confirmation of touchdown here.
Now, I am on the edge of the landing zone that we call the ellipse. It is a huge landing zone that is larger than the size of Rhode Island. And behind me are the helicopters that will be taking those recovery teams to the capsule once it lands. Now, these teams are prepped and ready to go. We're just waiting for that capsule to arrive.
As the SRC approaches the edge of Earth's atmosphere, we are just moments away from the world's largest ever asteroid sample return. Jim, what are you feeling right now?
I am literally tingling all over with exhilaration. This is a small step for a capsule and a giant leap for science.
It really is, and if that's one thing we can impart, that is it. This is a huge, huge milestone, a great achievement. So this is it. We are just 15 minutes away from the OSIRIS-REx sample return, a journey of 7 years and nearly 4 billion miles. The work of thousands culminates in this moment. Let's turn it over to our mission commentator, James Traley, to take us through the final moments. James, we're all yours.
Yeah, Lauren, buckle up and get ready for the ride of entry, descent, and landing. This is 13 minutes of crazy descent, punishing deceleration of our spacecraft, starting at 27,000 miles per hour when it enters into Earth's atmosphere, and eventually slowing to a leisurely 11 miles per hour as it descends and lands on the Utah Test and Training Range. And as the sun begins to rise in the west coast, the SRC is going to be streaking across the atmosphere above San Francisco, California, about 82 miles in altitude. It's going to be coming in hot, over 5,000 degrees Fahrenheit, almost a couple seconds after it hits that atmosphere. That's about half as warm as the surface of the sun, to give you some context. We're about 20 seconds away. You see the team at Lockheed now, ready on the edge of their seats. This team, I'll remind you, just a few hours ago, gave that command to release the SRC on this long journey. It's been on its own for 4 hours. There's nothing we can do at this point. It's coming in, rain or shine.
EO milestone. The SRC has entered the Earth's atmosphere. UTTR tracking assets have acquired.
And here we go. Start your stopwatch right now. We are 13 minutes of entry, descent, and landing. We have that expected milestone of entering into the Earth's atmosphere. We can see the team at Lockheed, and we actually have a visual now. This is from our infrared tracking camera on the WB-57, our high-altitude plane, at about 47,000 feet MSL, mean sea level, getting a great view of that SRC heating up as it enters into Earth's atmosphere. The punishing deceleration that spacecraft, that SRC, is experiencing right now, as it comes in at about 27,650 miles an hour. You can see it glowing brightly in the sky. And in just a few moments, we're going to reach peak heating and peak deceleration. That's at 32 G-forces, punishing G-force on our SRC. A phenomenal view of that streaking SRC coming in across the sky. At this point, we have entered in over San Francisco, California, and are very quickly going to be approaching the Utah Test and Training Range just a little bit further to the east.
EO milestone. SRC is experiencing maximum heating and maximum deceleration.
So you just heard right there, we're experiencing that 5,000 degree Fahrenheit maximum heating, burning scalding hot on that heat shield that is protecting our sample within, and maximum deceleration that is at 32 G-force, punishing deceleration from Earth's atmosphere, the drag forces that are acting on that SRC. Once again, as I mentioned, that sample is safe and sound within that SRC, that sample return capsule, as it comes in, burning through Earth's atmosphere. You can see our high-altitude plane searching for that SRC. You can see it faintly on your screen there. Our next milestone will be expecting that drogue parachute deployment. That'll be at about 102,300 feet altitude. And as I mentioned before, that will stabilize our descent and slow us from hypersonic to subsonic speeds as we continue to target the Utah Test and Training Range.
Expected EDO milestone. SRC commands drogue parachute deploy.
So we heard that command to deploy the drogue parachute. Waiting to see that visual confirmation, but that is at 102,300 feet. And a side note, at this time, 8:44 a.m. Mountain Time, the OSIRIS-REx spacecraft is at its closest approach to Earth. That will be on to its extended mission visiting the asteroid Apophis in the year 2029, continuing this incredible mission at another world. Our next milestone, we should be expecting main parachute deployment at around 8:49 a.m. Mountain Time. That will be at around 5,000 feet elevation. We continue to track with our high altitude camera here.
EDO milestone. We have confirmed parachute deployment.
Wow, and after an exhilarating streak across Earth's atmosphere, we have parachute deployment. You can see just a sigh of relief from the team. I can hear some applause here. There is that orange creamsicle colored parachute, just a delight, a sweet delight to see in our sky here over the Utah Test and Training Range. And now this is like a marathon runner savoring that last lap here as we approach the finish, that landing in the Utah Test and Training Range.
SRC has touchdown.
And touchdown of the OSIRIS-REx sample return capsule. A journey of 1 billion miles to asteroid Bennu and back has come to an end, marking America's first sample return mission of its kind and opening a time capsule to our ancient solar system. And the team can now breathe an immense sigh of relief. We now have the sample return capsule, the SRC, containing pieces of the asteroid Bennu. You see the reaction there just moments ago as they got that sample back on the ground.
Looks good, huh? Yeah.
Sit down, sit straight up.
Parachute right next to it. We did it.
Not even tilted over.
Did it.
Not even tilted over.
Yeah.
Beginning to install beacon covers.
Beautiful.
Motor safety huddle down. OSIRIS on 3. 1, 2, 3.
OSIRIS.
Congratulations to the OSIRIS-REx team. You did it. You designed it. You built it. And you carried out the first mission to collect a sample from an asteroid. And after a 2-year journey, it has touched down at the Utah desert. It brought something extraordinary, the largest asteroid sample ever received on Earth. This mission proves that NASA does big things, things that inspire us, things that unite us, things that show really nothing is beyond our reach. It wasn't mission impossible. It was the impossible became possible.
Right. Well, OSIRIS ended just like it began. Absolutely picture perfect. I mean, I actually think I'm dreaming. I don't believe it. I don't believe it. The capsule was feet from a road. It just stuck the landing. It landed and didn't move. Didn't look like it was spinning whatsoever. Very, very straightforward recovery operations. Absolutely. So thank you to everybody. The team has done an enormous job. This is what happens when you practice, 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 and practice. Everything goes perfectly. Couldn't be more proud of this mission. The team, the military colleagues out here that have been with us every step of the way have been absolutely wonderful hosts, wonderful support. I'm gonna kind of miss this place actually. I kind of settled in here and it's got a real charm once you get to know it. So. Thank you, Utah, for being our landing ground. Of course, my family, Kate, Xander, Griffin, wouldn't be the same without you guys here. It's been an amazing journey. My boys have grown up with the dad is the PI of the flight program on NASA, and that's no longer true. And I'm also really excited that we handed off and passed the torch to the next generation. I believe the divert maneuver went exactly as according to plan, and OSIRIS Apex is on its way to Apophis for the next chapter of this fantastic journey. And I cried like a baby in that helicopter when they told me that parachute had been spotted. I tell you what, man, it was the end of a long, long day. We've been up since about 1:30 this morning with spaceflight activities, and everything went according to plan. So I can't wait to see how they're doing over in the Avery. Hopefully they got that capsule nice and secured and on its way. There we go. Looks like they're getting ready to get to that back shell and see what the treasure looks like inside. So yeah, the best times are ahead of us. I always feel that way. We're gonna get in that canister. We're gonna reveal that tag sample. We're gonna see those samples of Bennu, and we are going to rewrite the history of the solar system with the material that we brought back here. Thank you.
The doors are now open. We are entering into the clean room, and that SRC is about to be moved off onto our clean room fixture. This is why we do science, right? To get these kinds of samples, every piece of dust and grain inside that sample return capsule is a PhD thesis waiting to be written. It's a new discovery waiting for us about the origins of the solar system and our place in it. And the vast majority of that sample, more than 70% of that sample, is actually going to be stowed away for future analysis. We did the same exact thing with the Apollo missions when we brought back rocks from the moon. A large quantity of those rocks and dust from the moon our astronauts brought back or stowed away for future generations with the expectation that our technology will continue to improve and improve and improve, and then we'd be able to ask questions that we couldn't even begin to fathom. And now the same thing we'll be doing with the OSIRIS-REx samples that we brought back from the asteroid Bennu. A lot of these will be opened up 50 years from now with scientists who are yet to be born, asking questions we can't even begin to imagine.
Wow, don't be afraid to clap or cheer. Today is a celebration. Welcome to the much anticipated OSIRIS-REx sample reveal.
So 7 years, almost 4 billion miles of a journey throughout the solar system. Now back, the sample return capsule landed in Utah. Right on the money. It was a picture-perfect mission. It's a feat of engineering. So, you ready to see the results of the mission? Take a peek.
Rocks tell you a story, right? And it's the story of Bennu and the history of the solar system that I'm most excited to unravel with the science program. And when we look at the materials, these clay minerals, these carbonates, you had a lot of water moving around in the early solar system beyond what we really expected from our meteorite investigations. You know, when we look at meteorites, we think water moving in very tiny scales, but I imagine a world right at the beginning of the solar system, right in that protoplanetary disk, where you had a lot of ice and a lot of rock and metal and carbon, and radioactivity started heating these things up, and you got massive circulation, what we call a convecting ball of mud, hundreds of miles across. And it's in that environment that I imagine these carbon atoms going through the first stages to the origin of life. And to me, that's the greatest mystery that we're facing right now, is like, how do you go from a ball of mud to something that's alive? Like, what happens when you make that transition? And the deepest desire is that we're going to make some progress in trying to figure out, what is it? Why is it that we're here, we're alive, we're conscious in this universe? It's such a gift that I hope everybody really stops and thinks about it every once in a while, no matter what your problems are in everyday life. The fact that you're alive and that you're aware on this beautiful planet is something you should be grateful for every day. And that's really where I hope my imagination takes everybody.
This is about the future generations. And Danny DellaGustina, who's now the PI of OSIRIS-APEX, I officially congratulated her right when the SRC released from the spacecraft. My PI ship follows the capsule, and she takes the spacecraft on to the next adventure. She started with us in 2004 as well as a freshman at the University of Arizona when she enrolled in my Asteroids seminar. And she led a student experiment design for a discovery version of what we called OSIRIS back then. She was going to be the student experiment lead, and she is strongly committed to bringing the future generations along with her.
Looking forward, we now know that Bennu is one of the most, if not the most hazardous asteroid in terms of its orbit. And so we're really sort of looking towards the future as well to examine how some of these near-Earth asteroids, how their paths are going to evolve relative to our own path in the solar system, and what sort of planetary defense measures might need to be taken as we just think about our existence as a species on this planet moving forward.